everyone, my name is Guillaume Vigoureux. I'm from the LPINS and I'm supervised by Benjamin Godard. And so my goal today will be to try to explain the observed nitrogen plus in the Milky Way. So first, what do we care about iron? The main reason is because of the star formation. Well, to be more precise, the star formation only occurs in neutral region, but when you look at the Milky Way, the galaxy, half of the volume is neutral and the other half is iron. So we need to understand how do iron region form. So there is two main ways to form iron region in the Milky Way. So it's due to the radiative energy due to the star radiation or the mechanical energy due to the star explosion. But in practice, we almost always neglect the star explosion, so the mechanical energy. Just to give you some hints, this is an example of star radiation region. So the three stars in yellow are stars, and you can see those bubbles which are due to the radiation of the stars. Okay, and so how to find those iron regions? So one thing that you need to know is that in the Milky Way, almost all the diffuse matter is hydrogen. And just when you look at this, so this is the ionization energy with respect to the atomic number, you can see that nitrogen is above hydrogen. This means that in the Milky Way, in the diffuse matter, the Milky Way, the N plus traces fully ionized region. This means that if you have N plus, it means that there is already H plus, which means that all the matter can be considered to be ionized. Okay, and in our case, Paul Goldsmith, an American astrophysicist, did a measure with Herschel, this is a space telescope, in 2015, of two lines in infrared of the N plus. Okay, and to be more precise, what he did is not only seeing two lines in the Milky Way, he did the galactic survey. So here you have an image taken from Earth of the Milky Way, and what he did, he just like taking a spectrum at each of the longitude in the Milky Way. So to show you the data of Goldsmith, those are the data. So as I told you, there is two lines, one in blue and one in red, and what you can see that he almost reaches all the longitude of the galaxy. And there is two interesting things in those plots, is that there is two regions on which there is only upper limit, which means that there is no detection, but you can know the upper limit thanks to the sensitivity of the telescope. And in the region between, so between minus 50 and 50 degrees, what you can see is that there is really strong variation. So you have the galactic longitude, and above it, let's say the abundance of the nitrogen. This is in log scale, and so you can see that there is almost 2 orders of magnitude of variation. So there are two interesting stuff. No N plus detected between minus 50 and minus 180, and the same in the other side, and just strong variation in the middle. Okay? When he did those measurements, he tried to compare them with model of star radiation region, and he found out that it wasn't coherent. So the point was, what was ionizing the nitrogen? So this is here that my PhD work really starts. So our guess was that the supernova remnant, so what we call supernova is explosion of stars, a remnant with this word to say that it's not the explosion at its very beginning, it's after like thousands of years. This is the reason why we say remnants. So, just to explain to you a bit more what are those supernova, this is an example of the stellar objects, or let's say the galactic objects, depending on their mass. So you can see that for very low mass, those are planets, then what we call brown dwarf, and then there is two kinds of stars, depending on their mass, and those two types of stars are due to the end of life. So I will just show you the end of life of all those objects. So basically, no explosion, the supernova for the smallest one, and for the first type of stars, there is sometimes supernova, and for the really big stars, above 8 solar masses, there is always supernovas. So we will focus on those two kinds of stars, but there are different types of supernovas. So this is an example of a supernova remnant. So this is the Crab Nebulae. So the center, which is gray, is in X-ray, so you can somehow guess that it was a core before, and the other part, which is in color, has been seen invisible with Hubble, and it shows you that the shock wave, due to the explosion of the star, is propagating in a really diffuse medium and creating all those kind of filaments. And to be even more precise, I can give you some order of magnitudes, because it's sometimes hard to understand at which point those are powerful explosions. So you have the energy of a supernova compared to the energy used by the whole population in 1 year. So this is like really intense and really energetic phenomenon. And then you have the medium in which those shocks are propagating. So ISM is the interstellar medium. So this is what is in fact black in the Crab nebulae. And so you can see that those regions are between 10 to the minus 2 to 10 to the 2 particles per centimeter cube. So this is really hard vacuum. So just to make a quick comparison, the line below is the what we call ultra high vacuum on Earth. So this is 10 to the 7. So we are saying that we have really strong shocks propagating in really diffuse medium. So the physics is quite really different from what we are expecting on Earth. So okay, so my work was mostly working on how to SNR ionized nitrogen. So our expertise at the LPNS is about the barogram shock code. So this shock code has been created 40 years ago, and it allows us to see the dynamical, the thermal, and the chemical evolution of a diffuse gas which is shocked by a really strong shock front. And as it's strong, I would say fast. So we are speaking about 10 km per second up to 500 km per second. So those are really fast shocks, which are the ones that we are expecting from SNR. Okay, so I will show you how the SNR is ionized by nitrogen. So here you have what is happening below 100 km per second. So in gray is the nitrogen, and in green is the nitrogen plus. So you have in red the shock front, so which is expanding in the middle, in which is really diffuse, and which is composed by only nitrogen. And when the shock front is propagating, it will condense and make the medium hotter, so it will create N+. Then this N+ will slowly cool down, radiates, and then recombine into N. So this is the way to form N+ in the slow shocks, basically just through collision in the inner part of the shock front. So this is for slow shocks. I will show you for fast shock what's happening. It's a bit more complicated. This time we are talking about fast shock. So the shock front is really hot, and this shock will radiate strong enough to ionize the surrounding gas. So you can see that just on the edge of the shocks it's already N2+. So this is the medium which has not been yet shocked, but just ionized due to the radiation. And so you can see that just a bit further there is even N+, and when you go even further there is no radiation left, so this is only neutral nitrogen. And the same phenomenon occurs. You have compression on the N2+, which is not really forming N3+, but then it will cool down slowly to form N+, and then the N+ will even cool down to form the neutral nitrogen. So there is two ways in fast shock to create N+, through radiation of the shock front and from cooling of the N2+, which has entered in the shock. So now that I have presented you the way to form nitrogen in SNR, I will show you at which point there is a lot of supernova in the Milky Way. So here we have several parameters of the rate of supernova in our galaxy, the type of supernova, their mass, their energy, many statistics, many parameters. And then I can show you a plot of all the supernova in the Milky Way. So this is our model. So you have the position. This is at scale. So you can see maybe the black cross, which is the sun, and you have many different colors which are representing the velocity of the shocks. So when a shock is really young, it will be really fast, so above 200 km per second, and when it will start to be old, it will be slowed up to 30 km per second. Just to show you, because it's maybe unclear why the center seems to be a bit different than the edges, maybe it's only due to the density of the medium. The center part of the galaxy is much more dense than the outer part, so when the SNR propagates into the medium, it will be much bigger in the outer part of the galaxy. So here you have just a zoom to see that there is many supernova with many different colors, meaning many different ages, and you can see that in the middle it's much smaller than in the edge. Okay. So here it's just to show you at which point, when you are looking at the Milky Way, considering that you have a certain beam, the same as Goldsmith, you will see a number of interaction between your line of sight and the supernova. So this is between 10 intersection to 100 intersection between the line of sight and the supernova remnants. And you can still see what I was saying to you before, that there is a strong sharp increase and a sharp decrease around -50 and 50, and then strong variation in the middle region. Okay, so now that we have seen how many stars, how many SNR we can see at each line of sat, and how the SNR are created N+, I can show you the mix of those two models, which is how much N+ is made down per line of sight. So here you have the two lines of the N+, so the points are the measure, and the lines are the models. So what you can see for the first line is that in the center part we are almost reaching the expected values, and you can see that in the outer parts we are still below the upper limit. So this is really coherent with the measure, and you can see that for the second line we are a bit further. But let's say that we are not that far. So but we will just conclude that by saying that the star explosion aren't negligible in the N+ formation. You can't explain the ionization of the nitrogen in the Milky Way without using star explosion. You can't only consider star radiation, and this is a major upgrade of the vision that we have of the ionization in the Milky Way and in the galaxy in general. And there is obviously still some upgrades to do, mainly about the radiation of the SNR in its inner part and the galactic distribution of the supernova. So, thank you for your attention.